Hello, today I'm going to be walking through a couple of the questions that Ms. Riendo didn't have the opportunity to explain or go over in class in detail on Friday from the first homework, so that having to do with analytically evaluating limits. So I'm going to be going over 2, 4, 5, 6, 8, and 9, and I'll just jump right into it. So question 2, this question should really scream out the moment you look at it that it needs to be factored. So before you really try and plug anything in, you want to just look at the top and look at the bottom because both of them can be pretty easily factored. So the top can be factored to x plus 3, and the bottom inside of the radical, you're going to be able to factor to x plus 3 squared, since this follows the basic form of a 2 times 3 plus 3 squared, which can always be factored into a binomial squared. So from here, the common mistake would be to immediately jump to limit as 3, limit as x approaches negative 3 of x plus 3 over x plus 3. But what's important to note is this denominator here, since you're squaring it and then taking the square root, this number is always going to be positive. So when you're taking the square root of something squared, it's not just that value, it's going to be the absolute value of it. And that's where this question gets complicated, because you want to just cancel these two out, but you can't necessarily do that. In fact, you have to evaluate this limit not just analytically by plugging in negative 3, but you're going to have to look at the right side of the limit and the negative side of the limit and compare the two. So starting off, we're going to look at the limit as x approaches negative 3 from the right of x plus 3 over the absolute value of x plus 3. So what's good about this one is as long as x is greater than negative 3, this absolute value isn't really going to come into effect. In fact, you can just ignore the absolute value signs since it's always going to be positive inside of it. And you're going to end up with being able to cancel out the x plus 3 terms. So you have limit as x approaches negative 3 plus just of x. So you end up with negative 3. Then I'm going to use some of this space. You want to take the limit from the left. So limit as x approaches negative 3 from the left of x plus 3 over the absolute value of x plus 3. Now, in this instance, you're going to be from the left of x plus 3. So this inside section is going to be negative x minus 3. And we're just going to pull that negative out and put it in the front. So you'll end up with limit as x approaches negative 3 of negative x plus 3 over x plus 3. And of course, you can just cancel these out. Then you're going to plug in negative 3, and negative 3 is just going to be 3. Now, you want to look and compare these. Since the limit from the left doesn't equal the limit from the right, graphically what's happening is from the right, it's going to negative 3, and from the left, it's going to positive 3. So if this is f of x, and you're taking, and this value is x equals 3, you're not going to coalesce to one value. And therefore, since these don't equal each other, you would say limit does not exist. All right, moving on to number 4. If y equals 7 is a horizontal asymptote of a rational function, then which of the following must be true? So immediately, you just want to think about what does a horizontal asymptote necessarily mean? And we go back to graphing it. If you imagine this is the graph, and this line is 7, then f of x is going to, at some point, the graph is going to get infinitely close to f equals 7. So it'll look something like this or like this. Now what's important is it can really, f of x, I'll make sure, write it there, f of x can be any value it wants so long as it ends up turning into this line y equals 7. So it can do this, it can do that, and it can go as far as it wants as long as some point it settles in to y equals 7. So we're going to take that information and look at the potential solutions. So limit as x approaches 7 of f of x, you have no information about that because that could be any one of these values since it can go wherever it wants in between the horizontal asymptotes. So it's not that one. The limit as x approaches infinity of f of x equals 7. Yes, since as x approaches infinity, at some point, since it's a horizontal asymptote, f of x needs to coalesce and end up just following infinitely closely that y equals 7 line. So this one is correct, but we'll look quickly at the other ones too. This one, same case as the first one. We have no information about x equals 0, so you can knock it out. No information about x equals 7, so cross that one out. And then limit as x approaches negative infinity. Nope, also we have no information there. We can assume that it's also going to follow x equals 7. It's going to follow y equals 7, so as x approaches negative infinity, it's going to equal 7, not negative 7. So that answer also is incorrect, so you're going to get B. Then, moving on to 5. This one, immediately you're going to want to find a way to simplify this because it's a little unwieldy in the form it is now. And the best way to do that is by getting rid of these reciprocal functions. So you're going to multiply the top and the bottom by x, which is the same as multiplying it by 1, so you're not changing the value of the function at all. Then, if we calculate that out, limit as x approaches infinity of x squared minus 1/2 over 2x squared plus 1/6. And in this situation, it's going to be really easy because you want to look at those leading coefficients, those leading terms, and it's the same value. So whenever they're equal, it's x squared equals x squared. You look at the ratio of these leading coefficients, which you can imagine there's a 1 here, it's going to be 1 over 2, or 1/2, and that's your answer. Now, number 6, yet again, this is one where you can factor. So at the top, you're going to factor out an x, get the limit as x approaches 1 of x squared minus 1, over x minus 1. Yet again, this one you can factor since it's different to perfect squares. So limit as x approaches 1 of x plus 1, x minus 1, over x minus 1. And here, you can just cancel these out. Typically, you would have to have a removable discontinuity here, which you would add into the function in some way. But since you're looking for the limit, the actual value at x equals 1 doesn't matter. So you can just cancel these out, don't worry about them, and you'll end up with limit as x approaches 1 of x plus 1. Then you can just plug in 1 and you'll get 2. Moving on to 8. 8, you'll end up doing a similar thing to what we did in 5. You're going to want to clean it up so it ends up being one of these much easier functions that you can work around with. So for here, we're going to multiply to get rid of this x plus 1, x plus 4 on the bottom, which is really ugly. You're going to multiply the top and the bottom by x plus 4. And this isn't completely necessary, but also to clean up this 1/4, which is going to be a little uncomfortable to play around with, we're going to throw a 4 in front too. So yet again, this entire expression is just 1, so you're able to do whatever you want with it, since the entire value does end up just being 1. So then if you multiply that out, this is just going to turn into 4 minus, and the 1/4 is going to turn into x minus 4. Then all of that over, if you run the numbers, you can get 4x squared plus 16x. Yeah. Now, once you're here, oh, that's the limit, sorry. Limit is x approaches 0 of that. Now, what you need to do is just do another round of factoring, simplification. Limit as x approaches 0 of top, which is going to be negative x, and the bottom is going to be x, since you can factor out the x, of x times 4x plus 16. And of course, you can cancel out these x's. You'll end up with limit as x approaches 0 of negative 1 over 4x plus 16. You plug in 0, and you'll just get negative 1/16. Now, for the last one, a little bit of nasty trigonometry. To start, you're just going to try plugging in pi over 4, because you never know if that's just going to give you a correct answer or just give you an actual value you can work with. So just start off with 1 minus tangent of pi over 4 over sine pi over 4 minus cosine pi over 4. Now the top is going to simplify to 1 minus 1, and the bottom is going to simplify to root 2 over 2 minus root 2 over 2, which are basic values on the unit circle. And that, again, is just going to end up being 0 over 0. And this is an indeterminate form, which means we want to go all the way back to the start and use L'Hopital's rule. Since if it's indeterminate, you can take the derivative of the top and the bottom, and that'll be the new value of the function. So we're going to change this to x equals pi over 4. The limit as x approaches pi over 4 of derivative of 1 is 0, negative secant squared x over cosine x plus sine x, some basic derivatives. We're going to simplify this a little bit easier for when we plug in pi over 4. So I'm going to turn that secant into a 1 over cosine squared. Negative 1 over cosine squared x over cosine x plus sine x. And at this point, you can luckily just plug in the pi over 4 to get your final answer. So negative 1 over root 2 over 2 squared over root 2 over 2 plus root 2 over 2. Now, it's going to be a little bit of difficult, confusing algebra from this point on, but this bottom section, you're going to square it, so you'll have 2 over 4, so 1/2, then 1 over 1/2, whole thing at the top is going to be negative 2. Then the bottom, root 2 over 2 plus root 2 over 2, which is going to be root 2, and 2 divided by the square root of 2, you're going to end up with negative square root of 2. And that is the answer. All right, so that covers all of them, and hopefully that was helpful.